I'm going to talk about the time estimation, pose estimation for infrastructure inspection. Okay, so inspections of the large and the vertical structures are difficult and they require for skilled worker and then special equipment like a bucket truck or something. So, but these days, people use a drone and then using the structure from motion software to build the 3D. Okay, and then this is the time for the making the 3D the structure in the digital format. But the issue is building the survey grade SFM model is very time consuming as resource intensive and also very expensive. Okay? So I'm working on the tower inspection right now, but I heard that in practice, they're not collecting the many images. So they just apply the drone and then collect some kind of key area that they are going to inspect. Okay, so they only to collect a few images and not the bunch of the images. So which means that we cannot reconstruct the entire tower model using this few images. So what we can do is we are register those images into the baseline model that we already built. So to do so, the image registration process is to find out the pose and the angle, so that we find out what area the images are captured. So we need to have some kind of we call this robust image registration technique. Okay? But there are some two big chains of the pose estimation. One is the absolute pose regression using the like a neural network deep learning model. We just regress the pose, which means images input, output is a pose. Okay, so images in, and the model is give you the pose. But the issue is that to training this model, of course, we need the large numbers of the images. We need to have a ground truth, pose and the image pair. So it's not very much efficient. Okay. So more popular way is the feature and the descriptor matching. So we extract the feature from the images. We are matching them and then get the 3D point, and then using the PMP and then PMP solver and then Ranza, we find out the pose of the images. But the issue is we already have a SFM model. To match the feature, we need to have some kind of this descriptor database. So the new images and then this is a database to matching this feature. We need those database, but think about that we are getting the SFM model from the commercial software. They are now providing those descriptors. And also, I have a software, but the baseline model is built by the different software. It's not easy to register those images. The other issue is if I presented this one, someone else is asked me what if we're using the GPS, RTK GPS, but we flew the drone in the tower. This is a cell tower, but there are lots of the magnetic interference. So RTK GPS is not enough to estimate the pose. So what we can propose is it's just a generalizable solution. All the SFM softwares provide images and then their pose without any descriptor. Using those pose information, we developed a method to register those images. So I'll show the detail in the slide. So our goal is to, the generalizable image registration technique to support some existing baseline SFM model. So basically, what we are trying to do is this is a baseline SFM model. We make the bounding box, and then we have a set of the new images that our method is automatically the bounding box of the new set of the images. That's our goal. Okay. So here's the proposal method. so as I said, SFM software provide images and their pose. We need to have those information, as well as if you collect the data from the drone, we can get the rough GPS location and then heading angles of the camera. So first step is the image retriever based on some geometric relationship. Let's say this is a tower. We know the camera angles and then GPS location. We just roughly guess what images are looking at the same area that we selected. And then once you select we call the baseline images, and then we get the shadow images, which is the images and the adjacent location. So because we are collecting the data in a sequential manner, we can get the closest images. So this is two images from the database. These are we are using this is for the constructing the using this. So we are using the custom the feature matcher and the descriptor. We get the 3D model, a 3D point from the reference and baseline images. And then this is a new images. So we are just matching the 2D and the 2D matching. So at the end, we get the 3D point using the triangulation because we already know the pose of this image from the baseline model, and then this is a new images. So we are just a 2D and the 3D correspondence. We get the pose of the new images. After this, we can once you get the registered the new images into the baseline model, we identify the region of interest. So I'll show the detail in the slide. Okay, so so this is the image retrieval process. Basically, the drone is a fluid, okay? And then so we know the angle, and then the angles of the baseline images. We just find out that they're the height difference. And also we find out that those difference, this is like a trigonometric geometric. So if those are height difference the same way that those are difference, we are saying that these are two images are looking at the same area. So once we the retrieval these images, so I already mentioned, so we extract this is the baseline images. We get the adjacent, the shadow images. So we are using these two images. So get the 3D point using the triangulation, and then with the new images, and then we match with these baseline images and the 2D correspondence. Using all this, once you get the 3D and then 2D with the 2D and 3D correspondence, we get the the pose of these images. Okay. So this is the experimental validation. So we are using the ETH3D, the benchmark data set. There are some 35, the high resolution images and their pose. Okay. What we can do is that we leave the warm images, and then those are the new images. And we are trying to register those images into the baseline model. So this is the result. We are using the Ashburn former and the Roma feature detector. So we will get the the minimum, so like a percentage, the error that is like a no. So this is like a distance error is around the 5 or the 1 centimeter because we are using this is for the benchmark data. So angular, the error is around the 0.1 degree. So this is for the, but this is for the absolute error. But this is the because the 35 images, we are scanned all the 35 images, and then we are draw the area on the curve. So if you see this one, this is the existing method. So our method is here, okay, which means 40% of the images are registered with a 1 millimeter accuracy. Of course, this one is a deep integration, which means this part is that they're using the image as a used for the building the one model. So they're doing the the bundle adjustment as well. So that's why accuracy is much higher than ours. If you see the 10 centimeters, ours is better, which means of course this is not the deep integration. We are using the commercial SFM model from the commercial software. We are registered the images, so accuracy is not comparable with the deep integration of this model, but around the 10 centimeter accuracy, our method is covers a relatively the good accuracy. So we did we tested this method in the real world, the power structure. We are using the drone. We are collect the data with the helicopter path. We collect the 400 images, and then we are using the 1,3D, the software. We used the Pix 4D, but it wasn't successful. So this is we collect the data, and this is this is the base images, and then we retrieve those images. And then same thing for here. We already have a SFM model. We took because we need to know the pose so that we are testing the performance. So we took one images to the set as a new images, and then registered those images into the model. So at the end, our accuracy is reached around the 6 centimeter. Okay, so this is the last slide. So why we are doing this? Because we are making some power inspection software right now. So we are using the 3D Gaussian splitting model to loading into the web platform, and then engineers can view this tower structure, as well as we add some kind of the AI feature so that they are segmenting all the tower component. Okay? So once you get the power component, that we are finding out the where is this asset and the where is the handicap. Okay? So this is the research is one of a function that we are going to implement in this software. Okay?